we've got close-up on D2L. Going through those, I kind of had a feeling that virtually every one of them is going to get asked about. So I'm just going to go through each and every one rather than ask which ones you want to see. It might save us a little bit of time. So we'll see how that goes. And yeah. All right. So number one, we're looking for the pH of a solution. So we have a titration here. It says it's titration. So we've got 100 milliliters of 1 molar HCl, and we're adding 30 milliliters of 2 molar NaOH solution for a titration. So first thing we want to do there is recognize that we've got a strong acid and a strong base reacting. And so that tells us a little bit about what our reaction is going to be. So we're going to have HCl, strong acid, plus our NaOH, strong base. And so those are going to neutralize each other and give us water. And then the salt that we're going to get is going to be sodium chloride. We have an acid-base reaction, so we can go ahead and do an ice box here. Okay, now because we're doing a titration and we're changing volume, since we're adding stuff, we're going to want to work in terms of millimoles, and the easiest way to work in millimoles is just take your molarity times the milliliters. That will give you millimoles. So for the HCl, we've got 100 milliliters of 1 molar solution. So that's 100 millimoles of HCl. And for the NaOH, we've got 30 milliliters of 2 molar NaOH. So that's going to be 60 millimoles. I don't really care about the water and the sodium chloride here because they have no acid-base properties. So since I have a 1-to-1 reaction ratio here between the sodium hydroxide and the HCl, we're just going to use limiting reactant, which is going to be the NaOH. We're going to use 60 millimoles of NaOH. You're going to get used up. It's going to be all gone, and that means that 60 millimoles of HCl are also going to be reacted. So I'm going to have 40 millimoles of HCl left. I'm not going to have any NaOH. And so all the pH calculations are going to be using that 40 millimoles of HCl. Well, because it's a strong acid, it's going to be completely dissociated. And so I know that my concentration of hydronium ion in there, H3O plus, is just going to be the same as the HCl. And so that's going to be 40 millimoles. So if we take our millimoles and divide by our new milliliters, which is 130, that will give me my new molarity of H3O plus, and that's going to be 0.308 molar. And so now I can take the negative log of that, because that's going to be equal to my pH. Negative log of 0.308, and that's going to give me pH of 0.51. So pretty low pH there, but you can expect that with a decent concentration of a strong acid. So the correct answer there would be E. Okay, any questions on that one at all? You feeling pretty good on that? We're doing space. All right, so number two. Very similar type reaction. We got the pH of a solution prepared by mixing 45 mils of 0.183 potassium hydroxide and 65 milliliters of 0.1 molar HCl is what? So for this one, we're going to have another strong acid, HCl, and it's reacting with another strong base, KOH. It's a very similar reaction. We're just going to get water. And rather than NaCl, we're just going to get KCl. The same basic properties. It has no acid-base properties because we have a strong acid, strong base. So we're going to go ahead and icebox this one as well. Now for the HCl, we take our 65 milliliters times our 0.1 molar, and we get 6.5 millimoles of HCl. For the KOH, we take 45 times 0.183, and we get 8.235 millimoles of that. We don't care about the water or the KCl here. So here we see that the acid is actually limiting, so we're going to be minus 6.5 millimoles there, minus 6.5 millimoles there, so I have nothing left at the end. And I have 1.735 millimoles of potassium hydroxide. at the end there. So same as before, we're going to calculate a new molarity. Since I have base left over, I'm going to calculate a new concentration of hydroxide, and that's going to be equal to the number of millimoles, 1.735 millimoles, over our number of milliliters, which here is going to be 110. And so that gives me 1.577 times 10 to the minus 2 molar of hydroxide. So I can calculate a POH from that. So that's going to be the negative log of 1.577 times 10 to the minus 2. And that comes out to be 1.80. And my pH then, if I subtract that from 14, so 14 minus 1.80, and I get 12.20, and that would be D. Questions at all on that one? We're doing okay? Pretty much the same. The only difference is we calculated an OH concentration, then we had to do a POH, and then a pH. We could have just as easily taken the OH concentration, found the H3O plus concentration with the KW, and calculated the pH. We would have got the same answer. All right, number 3. Number 3 says, what volume of this molarity of KOH is needed to neutralize a 25 ml sample of 0.0597 molar HBr. So if we look at the reaction, we've got KOH plus HBr, and that's going to give me water and KBr. And the reason I want to write down that reaction is because it tells me that I have a 1-to-1 stoichiometry between the acid and the base. And that means that the 2 moles of the acid and the moles of the acid and the base are going to be equal. And that means I can use this nice equation, which is molarity of acid times volume of acid is going to be equal to molarity of base times the volume of the base. And I don't have to worry about the stoichiometry here because it's a nice 1-to-1. So I put in what I know. Molarity of the acid is 0.0597 times my volume, which is 25 milliliters. And that's equal to the molarity of my base, 0.0485 times the volume of base. I don't know that. That's what I'm looking for. And so when I solve that for the volume of the base, I get 30.77 milliliters, which is 30.8 milliliters, and that gives us an answer of D. Questions at all on that one? Yes? Well, then you've got to account for the stoichiometry with something out in front here. So if you had a 2 in front of the acid, then you would need a 2 in front of the MB and VB because you're going to need twice the number of moles as you need acid. So, all right. Okay, number 5. 4. I'm not sure. Well, I'll try to fit. No, I'm not going to be able to fit number 4 on this page. Not without getting really scrunchy, and I don't want to do that. We'll go to the next page. All right, so number 4. So consider the titration of 25 milliliters of 0.2 molar benzoic acid with this Ka with 0.1 molar sodium hydroxide. What is the pH of the solution when 35 milliliters of sodium hydroxide has been added? Okay, so here's a case where we have a weak acid, benzoic acid, and we're adding a strong base. So we know that the acid is going to react with the base. So we have HBZ, that's just going to be my little abbreviation for benzoic acid. That's going to react with the hydroxide of the sodium hydroxide. and that's going to go to water and the benzoate ion, which is the conjugate base of the weak acid, benzoic acid. So we're going to icebox this. And again, since we are adding two different volumes together, we want to work in terms of millimoles. So because we're changing volumes, we want to work in millimoles. So we need millimoles of the benzoic acid, so we've got 25 times 0.2. So that's going to be 5 millimoles of benzoic acid. And we're adding 35 milliliters of 0.1 molar sodium hydroxide. That's going to be 3.5 millimoles of that. We don't care about the water. We do care about the benzoate here because it does have acid-base properties because it's the conjugate base of the weak acid, and that means that it's a weak base. So our hydroxide here is going to be our limiting reactant. So minus 3.5, minus 3.5. And don't forget here, we're going to have a plus. Oh, I wanted to dance to that. Plus 3.5. Okay, so carry on down here. We get 1.5 millimoles of the benzoic acid, none of the hydroxide left, and 3.5 millimoles of the benzoate. And now when we look at that, what we see is that we still have some of the weak acid left, and we've made some of its conjugate weak base. Well, if you have a weak acid and some of its conjugate weak base in solution, what do we have? We have a buffer solution, and we can use the Henderson-Hasselbalch equation. Okay, so remember, Henderson-Hasselbalch equation is pH is equal to pKa plus log, and it's always the conjugate base, so concentration of Bz minus over concentration of HBz. Okay, we've got to do a little extra work here. We need to find the pKa. So that's going to be equal to the negative log of our Ka value, which is 6.3 times 10 to the minus 5. And so our pKa here is 4.20. Okay, now instead of concentrations, if we want, we can just plug in these millimole values. And so we get pH is equal to 4.20 plus log 3.5 over 1.5, and when we calculate that out, we get a pH that's equal to 4.57, so that would be A. Questions at all there? Any questions there? Okay. Number 5 is a KSP problem. So we're looking for molar solubility of barium sulfate in pure water, and we're given a Ka. It's a pretty straightforward problem. So we're going to have barium sulfate, BaSO4. It's a solid. It's a slightly soluble solid, which is why it has a KSP. So that's going to be in equilibrium with barium 2 plus. And my sulfate 2 minus. We're going to icebox that. I got lots of solid to start with. No barium, no sulfate. I'm going to lose X amount of the solid. That's going to give me X amount of the barium and give me X amount of the sulfate. And so I'm still going to have lots of solid at equilibrium. And here I'm just going to have X amount of the barium and X amount of the sulfate. I set up my KSP equation. So I have KSP. It's going to be equal to the concentration of the barium times the concentration of the sulfate. I don't have to worry about any exponents here because I just have ones for my stoichiometric coefficients there. So that makes life really easy. And so when we set up this equation, we have 1.10 times 10 to the minus 10, boy, that's a lot of tens, is equal to X times X, which is equal to X squared. So I solve for X here by taking that square root. And again, X value of 1.05 times 10 to the minus 5. So the molar solubility is the amount of barium sulfate that you would lose there. So that's the molar solubility, 1.05 times 10 to the minus 5. It also represents the concentration of barium at equilibrium, and it also represents the concentration of sulfate at equilibrium. So that one value has lots of different meanings. Okay, questions at all on that one? Yeah?
Why are you allowed to just say lots per GAS?
Because when you have this, you have to have additional solid present to keep an equilibrium. And it doesn't. You could have 1 gram, you could have 10 grams, you could have 100 grams. It wouldn't change any of that. And it's also not part of the equilibrium expression, so we don't really care how much we have. But there has to be some left. So that's why we just write lots. Yeah.
If you said that this wasn't in water, this is something else, would it be different the way you do it?
Definitely. The KSP would be different because it's an aqueous KSP.
Okay.
Yeah. You would never see that in my class.
Okay. Always in water?
Yeah. All right. Number 6. 6, 7, and 8 gave some people fits. Mostly just number 8. 6 and 7 seem to be okay. So these, the next 3 questions here are all on this silver carbonate equilibrium here. So we want to know what is the equilibrium concentration of silver for this reaction. So we have Ag2CO3 going to 2 Ag plus a carbonate ion there. And so let's just set up an ice box for that. So lots of solid here. 0 silver, 0 carbonate. I'm going to lose some of that solid to dissociation. It's going to give me 2x of the silver, and it's going to give me x of the carbonate. I should still have lots of solid left after that's all done. That's going to give me 2x of the silver and x of the carbonate. Okay, my KSP, I'm just going to write this over here for room. You guys see what I'm writing? Okay. So my KSP is going to be equal to the concentration of the silver ion, and that gets squared because of the 2 coefficient. That's going to be times concentration of my carbonate ion, and we're given the KSP is 8.1 times 10 to the minus 12. So we have 8.1 times 10 to the minus 12 is equal to my concentration of silver, which is 2x, and that gets squared, times the concentration of my carbonate, which is x. So this works out to be 4x cubed. And so when I solve for x here, I just divide by 4 and then take the cube root, and I get an x value of 1.27 times 10 to the minus 4. Okay. Now this problem asks for the silver concentration, and we see that our silver concentration at equilibrium is equal to 2x. So concentration of silver is equal to 2x, and so that's going to be equal to 2.53 times 10 to the minus 4. It's just a little rounding issue why it's not 2.54. Okay, so that would be C for number 6. Everybody good with that? And then number 7, I'm not going to work out because I don't really need to. It says what's the carbonate concentration, and that's equal to x. So the concentration of the carbonate ion is equal to x, so that's going to be equal to 1.27 times 10 to the minus 4. Questions on 6 or 7? Okay, let's flip on over here and work on number 8. This review is going to use a lot of pages in this book. So number 8. So here we have a common ion type situation, but it's not qualitative, it's quantitative. We've got to see how having a certain molarity of the carbonate ion present affect the solubility of that silver carbonate. So we're going to put in a 0.02 molar sodium carbonate solution, and that's going to be a source of carbonate ion. That's going to suppress the dissolution of, or the dissociation of the silver carbonate. Okay, so we're going to set up our equilibrium reaction again. So we've got Ag2CO3 going to Ag plus, 2 of those, plus carbonate ion. We're going to do another ice box here because our conditions have changed. I've got lots of silver carbonate, 0 silver, and I've got 0.020 molar carbonate ion already present in solution. Okay, that came from the sodium carbonate. And so now we're going to lose X amount of the silver carbonate. I'm going to gain 2X amount of the silver, and I'm going to gain X amount of the carbonate. Should still have lots of solid left in the end. 2X amount of the silver and 0.020 plus X of the carbonate ion. Okay, so now we set up our KSP expression again. It's the same one as before. So we have 8.1 times 10 to the minus 12 is equal to concentration of my silver ion, 2X, that gets squared, times concentration of my carbonate ion, which is 0.020 plus X. Okay, now we notice that we do have a really small KSP there, and so we're just going to try this by ignoring that X. Okay, essentially it's close enough to 0, it's far enough away from the 0.02 that we're banking it's not going to affect its value very much. Okay, so that takes this, it simplifies it to 8.1 times 10 to the minus 12 is equal to 4x squared times, lost 2 there, 0.020. And now when I solve that for x, I get a value of 1.01 times 10 to the minus 5, which is in fact much smaller than 0.02. And that's equal to, that's how much my carbonate ion was added. This is asking for the silver concentration. So remember, the concentration of my silver ion is equal to 2x, and so that's equal to 2.01 times 10 to the minus 5 molar. Okay, so that would be answer D. So a lot of people in my office on that one. Any questions on that one at all? Any questions? Yeah, there's no rule. You can ignore it any time you want. You just got to check, and it may not work out. You got to then go back through and not ignore X. So, yep. Any other questions on number 8? Okay. Yeah, ignoring the X on KSP is a little trickier because of all the exponents and stuff. So it does get a little trickier. Number 9. Let's see. Will a precipitate form if 3 times 10 to the minus 5 moles of solid sodium sulfate is added to 1 liter of 0.005 molar strontium nitrate, and we're given the KSP of strontium sulfate. Okay, so I've got a source of sulfate and I've got a source of strontium. What we want to know, we know that a precipitate can form. Strontium sulfate is in fact a fairly insoluble salt. It's got a KSP there. What we want to know is, have we saturated the solution enough to get a precipitate with these concentrations? So that's what we're going to find out. So if we look at the equilibrium reaction here, the KSP for strontium sulfate, it's going to be strontium sulfate goes to strontium 2 plus a sulfate ion. So we can write a QSP for this. And remember, when you're writing a Q or whether you're writing a K, they're the same equation. We just don't know if we're at equilibrium here or not, so we're calling it a Q. Okay? If we called it K, it would still look exactly the same. But we don't know if we're at equilibrium, so we're calling it a Q. So my QSP value here is going to be concentration of strontium, which is 0.005, times the concentration of my sulfate, which is 3.0 times 10 to the minus 5. And when you work out that QSP value, you get 1.5 times 10 to the minus 7. Well, the KSP is 3.4 times 10 to the minus 7. So it's close. However, my QSP is less than my KSP. And so I will not get a precipitate here. I have not yet saturated the solution. Okay, so no precipitate because the Q is less than the K. Okay, and that means I don't have enough ions in solution yet to form precipitate. It's not going to take a whole lot more, but we're not there yet. Questions at all on that one? Yeah.
How are you able to use moles and molar?
Well, I have a 1 liter solution, so when I put that many moles into a 1 liter solution, it becomes the molarity. Yeah.
And then one little solution, you have to like actually figure out the moles, the other thing, or molarity, the other thing, whatever.
What's that?
And then 1 liter solution, you actually have to like work it out.
Yeah, if we had like a 2 liter solution, then I would have to divide the moles by 2 to get the molarity, yeah. I've actually done that on tests before. It doesn't go well. I try not to do that. Let's see, number 10. So addition of a common ion to a solution containing a slightly soluble ionic compound has which effect? Well, as we saw up here with number 8, when we added a common ion, we added that carbonate, that's a common ion, we saw that the concentration of silver was quite a bit decreased from what it was before. It's decreased by a factor of 10 actually. Just by adding 2 1/100ths molar of carbonate there, it decreased the silver ion concentration by 10 because it suppressed the dissociation of the solid. So it decreases the solubility of the ionic compound. Okay. Anytime you have that common ion in there, it's going to want to force that reaction back towards the reactants. Questions at all on that one? I think most of you probably, no, I don't think anybody asked me about that one. So I guess I didn't really need to put 10 there. I'll write 11 there. Okay, number 11 just needs you to think a little bit about common processes. Which of the following is a spontaneous process? So again, we want to think about spontaneous process. It means I don't have to add energy, or in this case, I don't have to remove energy either to make this thing happen. A, if we look at water freezing at room temperature, does water freeze at room temperature? No, it doesn't. What would you have to do to water to make it freeze? You have to remove energy from it to get it to freeze. Okay, and that's going to take work, and that's not spontaneous. A nail rusting when placed in water, does that happen spontaneously? Do you have to add any energy to make that happen? No, you put that in water, it's going to rust. Okay, so that's our spontaneous one, B. A flat tire inflating, that would be awesome. However, it doesn't happen that way. A teacher's office is cleaned. Does that happen spontaneously? If you've been to my office, you know it does not. Again, obviously not all of the above. Before we had Dr. G in our office, we had another professor in there. She's since moved down to Colorado. One of the nicest people I've ever met. One of the neatest people I ever met. And unfortunately, she had to share an office with Dr. McLaughlin and I, who are not the neatest professors. So she was always very good about it, but I had to have driven her nuts. So that was 11. I guess I didn't need to write number 11 either. Number 12. Number 12, we'll get some work done here. All right, so for a reaction at 523 Kelvin, we know that delta H is negative 225, and we know that delta S is negative 350 joules per Kelvin. What is the delta G, and is it spontaneous or non-spontaneous? So we've got a temperature, we've got delta H, we've got a delta S, and we're looking for a delta G. So we have an equation for that. We know that delta G is equal to delta H minus T delta S. Okay, so our delta G is going to be equal to our delta H, which is negative 225 kilojoules, minus my temperature, and we're given it in Kelvin, so that was nice, times my delta S. Now you got to remember, since we're working in kilojoules for the delta H, we've got to do our delta S in kilojoule units. So that's going to be a minus 0.350 kilojoules per Kelvin. So my kelvins cancel here, and when we calculate this out, we get a value of negative 42 kilojoules. So is it spontaneous? Yes, and we know that because we have a negative delta G. Very good. Questions on that one? All right. Number 13. Okay, so 13 again, just kind of inspection one on here. So we're looking for a delta S greater than 0, so it's increasing its disorder. So A, gas to solid. Increase entropy? Definitely not. B, going from a solid and a gas to just a solid. Probably not. We may have to do a calculation, but if I had to guess, I would say no, and that's really all this one is. This probably should say most likely has a delta S greater than 0. And then C is the correct answer here. We're going from 2 moles of liquid to 2 moles of gas, 2 moles of solid, and another 3 moles of gas. Does that likely increase the entropy? Yeah, I went from 2 moles of liquid to 5 moles of gas and a couple moles of solid, so probably. And then D says all of them are like that, and E is none of them are like that, so probably C. So didn't have to write that one down. I'm not going to have to write 14 down either. So 14, which of the following is true if a process is spontaneous? Is the Gibbs free energy negative? Yes, so we know A is right, and I guess that's really the only option. What about the enthalpy for the process being negative? Probably, but maybe not. There are endothermic reactions that are spontaneous, so not necessarily. The entropy of the system must decrease. No, actually that kind of goes the other way. If the entropy of the system decreases, it probably isn't spontaneous, but you never know. There's certainly plenty of examples where it decreases and it's spontaneous, because entropy is a pretty small effect. The gravitational constant of the universe decreases. That's pretty grand. It's like, hey, wow, that little reaction in the beaker was spontaneous, and the universe changed the gravitational constant. Probably not. System volume increases. Yeah, we didn't talk about that kind of stuff. So, correct answer there is A. Questions on that one? That's pretty straightforward. 15. So, consider the process I2 solid to I2 gas. If the reaction is endothermic, what can you say about its spontaneity? So, they give you some clues here, but you got to work some of them out. So we're going from I2 solid to I2 gas. Now we're told it's endothermic. Sorry. Every once in a while the smart ass just can't be held in. My wife would say it's never held in. Okay, so we're told that the reaction is endothermic. So what do we know about delta H? Positive. Okay. And we're not told anything about the entropy. However, we're going from I2 in a solid form to I2 in a gas form. So what do we know about delta S? It's also going to be positive. It's going to increase its entropy going from a solid to a gas. Now we're looking for the spontaneity. And so we know that delta G is equal to delta H minus T delta S. So we've got a positive value here for delta H minus a positive value here for T delta S, because T delta S is going to be positive since T is always positive and the delta S is positive. So what if I have we'll just talk about delta H. If I have a medium-sized delta H, what if I have a small temperature here, a low temperature? What's that going to do to T delta S? It's going to make it smaller than delta H, and so at a low temperature, if T delta S is lower than delta H, I'm going to have a positive number minus a smaller positive number. What does that result in? Positive number. I don't want a positive delta G, I want a negative delta G. So I need T delta S to be bigger than delta H. So what can I do to make T delta S a big number? High temperature. Okay, so at a high temperature, this becomes a spontaneous reaction. Now what high is just depends on what the value of H and S are. Okay, but it would be spontaneous at high temperatures. So that's why B is the answer. Does that make sense to everybody?
How do you know that the H is positive by the end of it?
Because we're told it's endothermic. So if it's exothermic, then delta H should be negative. I brought my cup of water down here.
I see it. It's on the computer.
Oh man, okay. It's like I know I did because I filled it up at the water fountain up here. Thank you. All right. Next page. We're moving right along. Okay, 16. All right, so I got asked this question a lot, not specifically 16, just a lot of these. It says, from the table of thermodynamic data in your book, this is because I didn't feel like putting in the tables on all these different problems because it just uses up a lot of space, takes up a lot of paper for just a set of practice problems. So that's why I just said, from the thermodynamic table in your book. And then if you looked at the equation sheet or the constant sheet, you'll notice that there was no thermodynamic data on there. I do not expect you to memorize the thermodynamic tables in the back of your book. Okay? For the problems that you need the thermodynamic data for, it will be on the problem itself, so you don't have to worry about looking up in the tables. The tables just took up too much space on the exam. All right, so for number 16, we're just calculating the standard entropy change for this reaction. So we're going to have CO2 gas plus 2 waters going to CH4 gas plus 2O2. Now you did have to watch this one. That water in this reaction is in liquid form, and when you look at the table, liquid and gas are going to be right next to each other. Okay, so when we look up our delta S values, we had a 213.8, 70.0, 186.3, and 205.2. All of those are in joules per Kelvin. Okay, so our delta S is going to be sum of the products minus the sum of the reactants. So that's going to be 186.3 plus 2 times 205.2. Okay, so that's my products minus my reactants, which is going to be 213.8 plus 2 times 70.0. And when we add all of that up, we get a delta S of a positive 242.9. This is one of those interesting ones because if you look at the reaction, we're going from CO2 gas plus 2H2O liquid to CH4 gas plus 2O2 gas. So we're actually going from a gas mole and 2 liquid moles to 3 gas moles. Oh, and we see it's a positive delta S. Never mind, that makes perfect sense. That wasn't the problem I was thinking about. There was one problem on here I was looking at, it's like, well, it doesn't make sense. It kind of goes backwards, and that's where the values come in. Okay, so that one's E. Any questions on that one? Any questions? All right. So that was 16, right? Yeah, okay. 17. So for number 17, it says, from the table of thermodynamic data in your book, calculate standard entropy change. We just did that one. Sorry, 17. Calculate the sulfide concentration in Ag2S, given that the KSP for this is equal to 6 times 10 minus 51. I'm not going to go through that one because we just did a bunch of KSPs and we're just going to run short on time, and I know 121 is coming in right after us. So, any specific questions on 17? You're just going to have a 2x and an x. You're going to get 4x cubed, solve for x, and you're all set. So the correct answer there is D, though. It does work out. All right, number 18. Number 18, again, table of thermodynamic data. Calculate the standard Gibbs free energy change. Very similar to what we did for the entropy one. And so we get CH4, actually it's the exact same reaction in reverse though. CH4 plus 2O2 goes to CO2 plus 2H2O. We look up our delta G values in the back of the book. We get negative 50.5. O2 is elemental, so it has a free energy change of 0. Our CO2 gas is negative 394.4. Our water liquid is negative 237.1. Okay, and then for our delta G, we just do sum of the products minus the sum of the reactants. So we have negative 394.4 plus 2 times negative 237.1 minus, and it's just going to be a negative 50.5. And when you crank all of that out, you get a negative 818.1. And that's going to have units of kilojoules per mole. So pretty high delta G. It's going to be at equilibrium. Its equilibrium is going to be way towards the product side, which you might imagine. This is the burning of methane. That doesn't really reach much of an equilibrium. You're not reforming methane during its burning. All right. Let's see, 19. Similar to the problem we did a little bit earlier. We're looking at spontaneity. We have delta G is equal to delta H minus T delta S. We're told that delta H is negative, and we're told that delta S is negative. So before we had a positive and a positive, now we have a negative and a negative. Okay, so this value, delta H, is always going to be negative, and I'm going to be adding a number. I'm going to be subtracting a negative number since delta S is negative and T is always positive. T delta S is always going to be negative. So I'm going to be subtracting a negative number. If the T delta S gets too big, then the delta H minus T delta S is going to become positive. So at high temperatures, it would become non-spontaneous. But as long as that temperature is low, it means I'm subtracting a small negative number, and that's going to keep the delta G negative. So that's why it would be spontaneous at low temperatures, but not at high temperatures. If you're having problems reasoning that out, just use the table that I gave you in class and put that on your note card. It's the easy way to do it. Okay, but it's a good thing to understand how to kind of work out those signs and how temperature plays in that role. All right, that was 19. Let's see, number 20, I can't really write out here. Well, yeah, I can. I'll write out 20. I'll write out the equilibrium equation here. So we got Ag2, CO3, so our silver carbonate again, it's back. Goes to 2 silver plus the carbonate ion. Okay, so I want to know which of the following statements is true. So, is it more soluble in water than in a solution of silver nitrate? If I put it in silver nitrate, I've got a source of silver from the silver nitrate that's going to drive that reaction back to the solid, and it's going to make it less soluble. So it's going to be more soluble in water than in the silver nitrate, because the silver nitrate provides a common ion. Is it more soluble in water than in a solution of sodium carbonate? And again, yes, it is. The sodium carbonate provides a source of carbonate, so it's another common ion, and again, it's going to drive that reaction back to the reactants. It's a Le Chatelier's principle concept here. For C, is it more soluble than in a solution of sodium nitrate? Well, sodium is not part of this reaction, nor is nitrate. So neither the sodium nor the nitrate interfere or interact with that solubility at all. They're complete spectators, and so it would have the exact same solubility in sodium nitrate as it would in water. And so the correct answer there would be just A and B. It's more soluble in water than it is in those other two solutions with a common ion. Questions at all on that? I had a lot of people ask me about that this week. All right. All right, into a little bit of electrochem here. So number 21, we want to know which of the following is correctly balanced. Okay, well first let me write out the correct answer. The correct answer here is C. So we have Sn 2 plus 2 Fe 3 plus goes to 2 Fe 2 plus Sn 4 plus. Okay, the first thing we want to check is it mass balanced? Do I have the same number of atoms on both sides? I've got a tin here and a tin here. I've got an iron here, or 2 irons here and 2 irons here. Okay, so it is mass balanced. Is it charge balanced? I've got 2 pluses and 2 3 pluses, so that's a total of 6 pluses for the iron, plus the 2 pluses from the tin. So I have a total of 8 positive charges in the reactants. Over here I've got 2 pluses for 4 pluses, and then another 4 plus from the tin, so that's also 8 total positive charges. So I'm both charge balanced and mass balanced, and that's why this one is completely balanced and is the correct answer. If you look at the other ones, A and B are both mass balanced, but they're not charge balanced. For A, you have 5 positives in the reactants and 6 positives in the products. That's not charge balanced. In B, you have 7 positive charges in the reactants and 10 positive charges in the products. So that is also not charge balanced. Okay, so that's why C is correct and D is not. All right. 20. Any questions on that one? I should ask real quick. Okay. So number 2, just a little bit of oxidation state there. Oxidation state of manganese in the permanganate ion. We know that oxygen has a -2 oxidation state, so has a total of -8. The sum of the oxidation states has to add up to -1. I've got 1 manganese to it, so the total of the manganese has to be a +7, because a +7 and a -8 are equal to -1. Since there is only 1 manganese, it has all 7 of those positive charges, or positive oxidation states, so the manganese here is a +7 oxidation state. So that was D. Questions there? Yeah?
Would you mind writing the oxidation state rules up there on the sheet?
There's 8 of them, so no, I'm not going to do that. It'll take up most of the page. They're in chapter 8 of our book, so yeah. All right, let's look at 23 here. So which is the reduction half reaction in the following reaction? So we've got zinc solid plus 2H plus going to zinc 2 plus plus H2. So we write out our half reactions here. We've got 2H plus going to H2. We've got zinc going to zinc 2 plus. And the only thing we really need to balance here are the charges. And so I need to have 2 electrons here, and I need to have 2 electrons here. And so our reduction half reaction is going to be the half reaction that has the electrons in the reactant. Reactant reduction. Think of it that way. Electrons in the reactant reduction. Okay, so this is my reduction half reaction. Yeah. Okay, so if you have electrons in the product, that's your oxidation half reaction. Any questions on that? Okay. 24. Okay, so we just learned how to do this the other day. It says to balance this in basic solution. This is the worst basic solution balance ever because you don't have to do anything to balance it in base. It balances exactly the same as it would in acid, and you'll see why here. So we've got BrO minus plus FeOH2 goes to Br minus plus FeOH3. Okay, so let's break these out into half reactions. I'm going to have BrO minus going to Br minus, and I'm going to have FeOH2 going to FeOH3. Okay, so those are my half reactions. Now I want to balance anything that's not oxygen or hydrogen. We only got 1 bromine and 1 bromine, 1 iron and 1 iron. Yeah, balanced. Nice. Now I'm going to balance my oxygens with water. So I got 1 oxygen here. I don't have any over here, so I've got to add 1 water there. And on this side, I've got 2 oxygens. And over here, I've got 3 oxygens. So I need to add a water over here. Now I need to balance the H's with hydrogens. I've got 2 hydrogens here, none over here, so I've got to put 2 H pluses here. On this side, I've got 2 hydrogens and 2 hydrogens. I've got 4 in the reactants. Over here, I've got 3 in the reactants, and so I've got to add H plus here. People a lot of times forget to multiply those hydroxides by those little parentheses multipliers there. All right, now I've got to balance my charge. I'm now mass balanced. Now I've got a charge balance. On this top one, I've got 2 pluses and a minus on the reactant side, so that's a total of 1 plus. And then over here on the product side, I've got 1 minus. So to go from a plus to a minus, how many electrons do I need to add to that plus side? I got to add 2. A lot of people say 1. No, 1 takes me down to 0, to neutral, and then I got to add another one to get to the minus. Okay, so I'm going to add 2 electrons over here. And then over here I have no charge in the products. Over here I have a single plus, and so I've got to add an electron to that side there. So now I should be mass balanced and charge balanced in both my half reactions. And now I just need to multiply them by the lowest common multiple. I've got 2 electrons and a 1 electron. So I can just leave this top one alone, multiply by 1. This bottom one I want to multiply by 2. So that gives me 2 waters, 2 iron OH2s, 2 iron OH3s, 2 H pluses, and 2 electrons. And so now my electrons cancel, my H pluses cancel, that water goes away, and that 2 goes away. And so now I'm left with H2O plus BrO minus plus 2 FeOH2 going to 2 FeOH3 plus Br minus. Okay, and if you check the charge balance on both sides and check the mass balance on both sides, you'll find that this is in fact balanced. Now it says to balance it in base. However, our next step would be to balance it in base, would be to add OHs to both sides to counteract the H pluses on whichever side it's on. But we have no H pluses left, so you can't do anything. So this is the balance in acid and in base as well. So that was a terrible problem to ask about being in base. But the question asked, what is the coefficient of the bromide ion? And we see that it is in fact 1. Okay. Questions at all on that one? All right, last one. Perfect timing. You know what happens when you tell your best friend to go take a hike? You get bro minus. Delayed effect there. All right, last one. We got permanganate ion plus I minus going to Mn2 plus I2. We're going to do this in acid. So we've got Mn04 minus going to Mn2 plus. We've got I minus going to I2. Okay. Balance anything that's not oxygen or hydrogen, so I need to put a 2 here. Balance the oxygens with water, so I'm going to need 4 waters here. There's nothing in that one. Balance the H's with H plus, so I need 8 H pluses there. Now I need to balance the charges with electrons. I've got 8 pluses and a minus here, so I've got a total of 7 pluses in the reactants on the top one, and 2 pluses on the product side in that top one. So I need to add 5 electrons. Sorry I'm rushing through this one a little bit. I've got another class in here in a minute and a half. Okay. Down here I've got 2 minuses in the reactant, no charge in the product, so I need 2 electrons here. So I need the lowest common multiple, that's going to be 10. So I multiply this top one by 2, this bottom one by 5, and I'm not going to write out everything because I'm out of space here, but what you end up with is 16 H plus 2 MnO4 minus plus 10 I minus going to 5 I2 plus 2 Mn2 plus 8 waters. And the question asks, what's the coefficient of iodine, I2? And we see that it's a 5, and that's why E is the correct answer there. All right.